All right, class, let's try it this way. I did want to use our notes from class, so I don't have to write so much on the board. It takes up so much of the space. So we're going to try it this way. Okay, so chapter 3 is all about exponential and logarithmic functions. So that's what we're going to do today. What we're doing is simply reviewing what you've learned already in your algebra classes, right? So nothing about the calculus in 3.1 and 3.2 is just a simple review of exponential functions, right? So unfortunately, we're dealing with an exponential function in this crisis right now as well. So it's a good time to remind ourselves of what this means. An exponential function is definitely one that has the variable in the exponent, hence the name exponential function. Now, many exponential functions, aside from the fact that they have a base raised to some exponent, they also might have a number multiplied here to the front. And that's what we want to go over. What do these numbers mean? Well, this a value right here is really the initial or the starting value of the function. And the reason for it is because definitely in this function, exponential function, if I should plug in x with 0, and of course most exponential functions are really functions of time, but if I should plug in a 0, so what I'm saying is I might as well have called it a t instead of an x for the variable, but if I plug in a 0 here, b to the power of 0 is equal to 1, so you get a. So this is why a is that initial or starting value for your function, right? So you start at this point a, and then that amount would either start growing or it will start decaying. It all depends on what the base is. The base tells you how fast something is growing or how fast something is decaying. Now, I put here that the base is a 1 plus r. And what does that mean? Well, if the base would be a 1, in other words, there you go, there's no r, any exponential function with a base of 1 is really not an exponential function. Why? And let me write this down. So if you have a function like this that has a base of 1, well, 1 raised to any exponent is nothing but 1. So that's really not an exponential function, right? It's a constant function that stays the same. And even if you should have an a value here, fine, it stays constantly at that level, right? So really what we're saying is if things are not changing, they are staying at 100%. So 100% means 1 means everything, right? Now, if something is growing at 105%, which simply means that it's not staying the same, it's going to be growing, yes? So if this value r is more than 0, it's in other words a positive, yes, then your base is more than 1, so you will be getting an exponential growth. If your base is negative, so something less than 1, so you're going to be always left with less than 100% of what you had, then your function will be decaying, yes? So as I put it here, r is the percent growth or the decay rate, written as a decimal. B is the growth factor or the growth multiplier. Since powers of negative numbers behave strangely, we'll limit b to positive values. What does that mean? So I'm going to explain this to you. So if we have any exponential function of any base, I'm just going to put it that way, and I'm not going to put that initial value of a. What you have learned, first of all, we already talked about the fact that b better not be equal to 1 because that's really not exponential. It's just going to stay that way, right? And then the other thing that we want is that we want that base to be always a positive number. So any exponential function has a base that is positive. And the reason for it is because we want x, in other words, the domain of this function, to be all real numbers. In other words, we would want the exponent to be whatever we want it to be. And sure enough, you know, if you have a negative base, let's say, I'll put this on the side. If you have a negative base, let's say -2, right? And we have that for a base and we want to raise it to any power we want, let's say 1/2, then what would that equal to? 1/2 exponent really means a square root, and all of a sudden this is not real, right? So you can't have non-real numbers whenever you talk about functions, because where are you going to plug that in on the xy plane? So because of that, and again, that's just a side note, we don't want to spend too much time talking about it, but we want the domain of any exponential function to be all real numbers. This is why we restrict the base to positive values. Now, as I said, that base could be more than 1 or less than 1. So if that base is a value more than 1, because this r was positive, right, so the percent growth is a positive, then we would get what's called an exponential growth. And if that base is something less than 1, and again, what do I mean by less than 1? Definitely still positive, so a value in between 0 and 1, then we get what's called an exponential decay. And that's what we want in today's situation, okay? And I can even go over that a little bit with you. So let's look at these two functions. One that has a base of 2, and one that has a base of 1/2. So these are really the easiest exponential functions to draw. So this is what I'm going to have. Before we even draw it, let's try and make a table of values and see what happens to these exponential functions. So if x is 0, remember we wanted the domain to be all real numbers. So I'm going to pick 0. So 2 to the power of 0 is 1. If you plug in a 1, 2 to the power of 1 is 2. Plug in a 2, 2 squared is 4, and let me put in one more, 2 to the third is 8. So really what this exponential function says is that your values are doubling every part of the time. So if x is in years, then they double every 1 year. If x is in days, then they double in every 1 day. If x is in minutes, then the values double every 1 minute. So for every time increment or x increment that you grow, as you see, these y values double, okay? Now, if you should have a negative value, because we said the exponent could be anything it wants to be, 2 to the power of negative 1 is 1/2. 2 to the power of negative 2 is 1/4. So that should give us here plenty of values to be able to draw the graph of this function. So I'm going to plot these points 0, 1, 1, 2, 2, 4, 3, 6, 7, 8. And I know my units aren't very nice. But here, negative 1 with 1/2, negative 2 with 1/4. So what happens to this? At some point, it starts growing out of proportions, right? Kind of, it blows up, and it just grows so much faster, right? Because it keeps doubling, and you're doubling a larger value every day or every hour or every year, whatever your time or your x constraint is. But on the negative side, as you see, would we ever get negative values out of this function? The answer is no, because even when we pick negative exponents, what we get are smaller and smaller and smaller positive values. A positive base raised to any exponent, even negative, is just a tiny, tiny bit. So that's what we would call exponential growth. Yes, the base is more than 1. And let's try this really quick for the 1/2 to the power of x function. Let's see what the y values look like. So I'll try the same thing here. 1/2 to the power of 0 is equal to 1. 1/2 to the power of 1 is equal to 1/2. 1/2 squared is 1/4. 1/2 to the negative 1. Again, remember, negative exponents simply take the reciprocal of the base. So 1/2 to the negative 1 will be a 2. 1/2 to the negative 2 would be a 4. So plotting these points, you would get 0, 1. Here, let me make it in red. 1, 2, 2. What did I have? I was just graphing something. I was just thinking of something else. So 0, 1. 1 goes with 1/2. 2 goes with 1/4. Negative 1 goes with 2. Negative 2 goes with 4. So it's really the reverse of the graph from before. Really, just as a side note, 1/2 to the power of x is the same thing as 2 to the negative x. Remember, the negative exponent makes the 2 go in the denominator. So what you might have learned in your college algebra classes on transformations, that if you plug in an x, substitute an x with a negative x, what happens to the graph is that it gets reversed, it gets flipped over the y-axis, right? All your positive x's are now negative x's. So that's what we would call an exponential decay function. As you see, the base is less than 1, and that's what we would call an exponential growth function. So what I was really thinking about in my mind earlier is just really the situation that we are finding ourselves in these days with the coronavirus. So right now it says that one person gives the virus to about 2 point something, almost 3 people. So what this means is that our base, let's say it's about 2.5, yes? So as you see, probably the graphs, is that the exponential function now, we just not doubling, right? But 2.5 times the values every day, yes? So what we would definitely want to do is not have one person share the virus with an average about 2.5 people, but obviously less. So if you even think about, let's say, trying to limit the amount and have the base be a 1.5, then an exponential function with a base of 1.5 is not as steep. So what is going to happen is our exponential function will start looking like this, right? So it grows slowly. So if it was this way up until now, what we want to do is from now on try and make it grow slower, yes? So we don't go up so fast, right? So it takes us longer to get there. What would be even better if we could take this and have the one person share it with less than one person. So if you give it, in other words, what? For every 2 people, let's say my base is now 1/2. That means what? Every 2 people only get to infect 1. Or even better, every 3 people only get to infect 1. So what happens if the base turns now less than 1? We can make the curve start going down because now the base is less than 1. So we have an exponential decay. So we are trying to slow down this growth and eventually make it do what? Start going down, yes, and well, make it disappear. So then nobody shares anything anymore, which is why all this social distance is talk, right? So we want that curve to go down and not up. So we want the base to be less than 1. Base being how many people are being newly infected, yes? But if the virus doesn't spread, then we won't be infecting anyone. So sorry about that mathematical reminder of what's happening today, but I thought it's really fitting in us talking about exponential functions. So I'm going to stop this video right now, and I'm going to move on in the next video.